So now we discuss solution of uh, discretized or rather partially discretized equations. So in equilibrium problems we have seen the nodal variables were independent of time. So there we got simultaneous linear equations. Here the nodal variables are dependent on time, and you have noticed that space has been discretized but time has not been discretized. So we have got ordinary differential equations in time, and we have to find out solution of those ordinary differential equations. Here we assume that ktt equal to 0, so we are getting only first order equations. If ktt is not equal to 0, then we get equations which you have already seen in finite element applications in vibration problems. So we are not discussing it here. So here we have two different ways of finding out the solutions in time, and one is mode superposition and other is time integration scheme. So in mode superposition, first we'll discuss mode superposition. So this is our starting equation where ktt matrix is null, so we are starting with this equation, and for the sake of convenience we are clubbing this 2 and calling it k. So though this is k and this is ks2, we are calling it k, but keeping in mind that this includes both k and ks2. So this is our starting point. So what is done in this modal superposition, that we'll see here. So in mode superposition, first we start with the homogeneous equation. That means first we start with r equal to 0. So this is the homogeneous equation, and you know this is an n by n matrix where n is number of degrees of freedom, and here per node there is a single degree of freedom, so this is number of node itself. So now if you assume a solution phi equal to phi bar e to the power lambda t of this equation and you replace it here, then you get this eigenvalue problem. So this is eigenvalue problem. So there are n eigenpairs, that is n eigenvectors and n eigenvalues. So this is the eigen problem, and suppose phi bar j is the eigenvector, then corresponding eigenvalue is lambda j. So this is what we get. And if phi bar l is the eigenvector, then this is lambda l is the eigenvalue, and this is what we get. Now suppose you pre-multiply this with phi l transpose and pre-multiply this with phi j transpose. So, and if you subtract, then your k is a symmetric matrix, so it does not matter whether you keep your phi bar at the beginning or phi bar l at the beginning or phi bar j at the beginning. So these two terms are equal since k is symmetric. So the left hand side is 0 and the right hand side is so k and kt not only symmetric, they are also positive definite. So if that is so, then your lambda has to be negative. Your lambda has to be negative. That we'll see just a little later. So now if you subtract, left hand side will be 0 and this is the right hand side, and since the jth and lth eigenvalues are different, so if this has to be 0, then this has to be 0. So that means if L and J are different, then this is 0. But if L and J are same, then this is 0. So this is 0, then this is not equal to 0. So if L and J are same, this is greater than 0 because KT is positive definite. Since KT is positive definite, so this is greater than 0. So for L equal to J, this is greater than 0 because this part is 0, and for L not equal to J, this is 0. So this is the orthogonality property, and this is not equal to 0, but we can make it, so suppose this is some positive value, but we can make it 1 by dividing this and this, both are same because L equal to J, this and this by square root of the value which we are getting here. So that is called orthonormalized. So if you orthonormalize, then this is equal to 1 for L equal to J, and this is called, the eigenvectors are KT orthonormalized. That means they are orthonormalized with respect to KT. Now suppose here, so if you see this term which you have already got, then this is minus lambda j phi L transpose KT phi j, and this is 1. That means this is actually minus lambda j. So if you remember, we are starting from here, and if you pre-multiply by phi j transpose, you get phi j okay, yes, if you are, so you are starting from the first one, and if you are multiplying it with phi L transpose, so this is what you get, and phi L transpose KT phi j is equal to 1 for L not equal to J. So phi L transpose K phi j is equal to minus lambda j because this is 1. So this is equal to, so either, so for L not equal to J, this is minus lambda j, and for L equal to J, this is 0. So now we know that if this is orthonormalized, this is equal to 1 for L equal to J, and this is equal to minus lambda j for L equal to J, and for L not equal to J, this is 0, this is also 0. So again I am repeating, so if J is equal to L, then this is 1 because this is KT orthonormalized, but this is not K orthonormalized. So when you do this for K, then you will not get when L equal to J, you will not get, for L equal to J, for L equal to J, this you will not get 1, but you will get minus lambda j. And since this is K is also positive definite, these two are same. If this is positive definite and these two are same, the right hand side has to be positive, so lambda j's are negative. So lambda j is negative. Now if you go to the actual equation, So this is the actual equation. This is the actual equation. This is the actual equation. So now you assume, now you may not take all the modes. You can take up to mth mode, where m is less than n, and you assume a solution of this form. We are again using the same symbol phi for the solution. So for the homogeneous part also we assumed phi to be the solution. For this also we are using phi as the solution. So keep it in mind. So this is the constant, this is a, sorry, not a constant, this is the coefficient multiplied by the eigenvectors. So coefficient, some coefficient multiply the first eigenvector, the second coefficient multiplied the second eigenvector, plus the third coefficient multiplied by the third eigenvector. So in this way it continues. So this is actually the modes are getting summed after being multiplied with a coefficient. So some sort of superposition of modes. So if you write it in matrix form, this first phi 1, then if you write the phi 1 vector, the phi 2 vector, phi 3 vector up to phi m vector, then here the coefficients will come c1, c2 up to cm. So if you call it p, then it is p multiplied by c. So now you know that kt, so this is phi equal to pc. So you pre-multiply this by p transpose kt, so you get p transpose kt phi, and you multiply it by p transpose ktp. So this is actually an identity matrix, because you know phi 1 transpose phi 1 transpose kt phi 1 equal to 1, but phi 1 transpose kt phi 2 is equal to 0. So you can verify that this is actually an identity matrix. So C is actually P transpose KT phi. That means C1, C2 up to Cm is equal to PT P transpose KT phi 1, phi 2 up to phi n. Phi 1, so these are the elements of phi. So these are not the separate vectors, these are the elements of phi to n. Okay, because this matrix is actually n by m, so this is transpose, so this is m into n, this kt is n into n, so we get m into n, and this is n into 1, so we get m into 1, and in the left hand side also we are getting m into 1. So if you take the initial conditions, so these are the actual initial conditions or the initial conditions in the physical space, and these are the initial coefficients in the modal space. So now, so this is our starting equation. So this is our starting equation. So here you assume phi dot as c, this will get differentiated. So ci dot t phi bar I, and summation is implied over the repeated index. So you get this dot t phi, and this is cit phi I, and this is 0. Now you just pre-multiply it with phi j transpose. So phi j transpose here by here, made mistake. So this is bar, this is bar, okay, this is bar. So now this c is a scalar, so you can take it anywhere. So here taking it here, this c we are taking here. So now this, so if j equal to I only, then it is 1, and this is minus lambda I. When j equal to I, this is 1 and this is minus lambda I or minus lambda j. So because I equal to j, so Cj dot minus lambda j Cj is equal to plus phi j transpose r equal to 0. So now the equations have got decoupled. So now the equations are decoupled. So this is the jth equation. So take phi 1, phi 2, phi bar 1 is the first eigenvector. Then you make phi 1 bar transpose k2 phi 1 bar. So this would be 1. Then this is minus lambda 1. This is again phi 1 bar r. Then 2. And in this way all the equations will get decoupled and you get equations like this, which you can solve independently. So since this is a single equation, you can solve it. So now and once you solve it, but you need initial conditions because this is a first order equation in time, so you require initial condition. So using this from the initial condition will be given in the physical space, so you get the initial condition in the modal space by using this relation, because you know this matrix, and then you put it here and you find out the Cj's, and once you get the Cj's you get the phi's by using this relation, phi equal to Pc. So here is one example. One they have taken this from Jean-Morgan's book. So this is a 1D heat unsteady heat conduction with generation term in the region x between 0 and 1 is governed by the equation this. Boundary condition is phi equal to 0 at x equal to 1 and x equal to 0 and x equal to 1, and initial condition is this. So it is required to determine approximate solution for the resulting temperature variation using 4 equal piecewise linear elements in x direction when k equal to 0.01. So the first two rows and columns, they getting deleted because phi 1 equal to 0 and phi 5 equal to 0. We have discretized the domain using 4 elements, so there are 5 nodes, 1, 2, first element between 1 and 2, second element between 2 and 3, third element between 3 and 4, and fourth element between 4 and 5. So first and fifth goes because it is 0. So because values of phi are 0 there, so you are left with this into this is equal to this. So this is our kt, this is our k, and this. So first we have to make it 0 and get the eigenvalue problem. These are the eigenvalues and these are the eigenvectors. So you have to kt orthonormalize the eigenvectors. So you multiply, suppose you want to kt orthonormalize phi 1 bar, then what you do? So you multiply this like this, you would get something greater than 0 and you are getting this. So you divide this by square root of this and you get this. Now if you use this phi 1 bar to get this, you would get 1. So in this way phi 2 bar when normalized it becomes this, and phi 3 bar becomes this. Now use this to decouple the equations as we have done. So these are the decoupled equations. So here minus lambda 1 comes, here minus lambda 2 comes, here minus lambda 3 comes. So these are the equations. Now you have to solve these equations. In order to solve this equation, you have to get your C1, C2, C3 0 from phi 2 0, phi 3 0 and phi 4 0. So how do you get that? That you get from this initial condition. So phi 2 means at 0.25 because you have divided it into 4 elements. So the second node, that is node number 2, is at 0.25, 25.75, yes, 0.25. So 0.25, so put this is 0.25, this is 0.75 by 2. So that's what we have done. 0.25 into 0.75 by 2. This is this, this is this. Now you get C1, C2, C3 at time t equal to 0. So from that you get the solutions for C1, C2 and C3. And once you get the solution, you get your phi 2, phi 3, phi 4 by using this relation. So this is the example.